Yes, sir.
Yeah. So this part you understood, right? So in case of a coaxial cable also, within the inner conductor and completely outside the coaxial cable, there will not be any electric field intensity. So there will be electric field intensity only between the conductors. So this is the expression. This you need to remember it actually. So we'll try to solve some problems related to this topic also. So this gives the expression for electric field intensity in between the conductors. So we'll move on to the next slide. So we'll try to discuss a new concept called electric potential here. So the moment once you are familiar with electric field intensity, electric potential is very easy to understand. And electric potential is basically nothing but voltage in your network language. So electric potential and voltage both are. So when you consider the electric potential definition, this is nothing but the work done in order to carry a unit positive charge. So first try to understand the concept behind that. So there is a charge located here of magnitude q coulombs. Now what will happen because of this charge, you know that there will be always some electric field present nearby this charge. So what I will try to do, I will try to bring a new test charge of magnitude qt and I was exactly placing at this point. So what will happen right now here? So since already there exists a charge of q coulombs and you are introducing a new test charge, so this test charge can experience a force because of the Coulomb's law. So what is the amount of the force experienced by the test charge qt is equal to, so let us say it is at a distance of r. So the amount of the force experienced by qt is nothing but qt into q divided by 4 pi epsilon into r square. So I can simply write this as qt into, so q by 4 pi epsilon r square is nothing but the electric field intensity exists at this point. So in simply I can say that the moment once I bring a test charge into a particular medium where already some electric field is existing, so the amount of the force experienced by the test charge is nothing but qt times the electric field at that point. So this is in the form of Lorentz form. This is also called as Lorentz force. But actually speaking, the Lorentz force and the Coulomb's law of force both are same. So we have studied the Coulomb's law whenever there are two charges. But what Lorentz force says? Lorentz force will says that a test charge can experience a force whenever it is placed in an electric field. So what the same kind of Coulomb's law we have represented in this particular format. So the Lorentz force says when you place any test charge in electric field, it experiences a kind of force. So is that concept clear? First part. Right. Now,
Yeah, that direction of the force.
direction of force is same as the direction of electric field intensity.
Okay.
So when you consider any point in the space, what will be the direction of electric field intensity at that point? That is the same direction of force. Now see here what I was trying to do. So let me say I was placing this test charge at this particular location qt. So already some force is existing here. Now I want to move the charge from point B to point A. What should I do? So suppose I was standing on a something like this. What will happen? Already there exists a gravitational force, right? Now I want to move from one position to the other position. Means I need to do some kind of external work in such a fashion that the gravitational force I should be able to nullify. In the same fashion, already there exists some force on the test charge qt, but still you want to move from one point to the other point means you need to do some amount of external work done, right? So we know that the differential amount of the work done you have to do, it will be the applied force multiplied by the distance. Force into displacement is called the work done. So how much force you need to apply in this case? So you need to apply a force such that whatever the force existing at this point should be nullified. So which means that you need to apply an opposite Lorentz force to cancel that, and then you are trying to cover a distance of dl. So this dw represents, sorry, this is a scalar. This dw represents the differential amount of work you need to move in order to move from point B to point A. So you need to apply a force that will be cancelling the Lorentz force. That is the reason why it should be minus qt into E. So this is of the form, you can say minus qt to E into dl. Let me write like that once again. So the total work done will be straight away. So instead of considering a differential length of dl, if you want to find out total work done from one point to the other point, you can integrate it. So hence w becomes minus qt into integral E dot dl. So this represents the amount of the work done you need to do in case of some electric field existing in that medium. But what is the definition for electric field intensity given here? So the definition for electric field intensity is basically nothing but the work done in carrying a unit positive charge. So the moment once you assume qt is 1 coulomb, the amount of work done will become the potential. So hence the electric potential is nothing but the work done per unit charge is straight away same as minus integral E dot dl. So this represents the expression for your electric potential. And since it is a dot product, you can see
Hello.
here, yeah,
Why that negative?
negative sign I already told you, right? Because the moment once qt is placed in electric field, it experiences some force.
Okay.
That force is given by the Lorentz force. Now,
Mm.
I want to move this test charge from one point to the other point. See, suppose when I was standing on the floor, already there is a gravitational force. Now I want to move from one point to the other point means you need to nullify the force, right? First of all, suppose when there is already some force existing, you cannot move.
Okay. Okay.
Am I sensible?
Yes.
Yeah. That means there should not be
Yes.
any
Yes. Yes.
force existing in on that position. So which means that you need to apply a against force, right? So whatever is pulling you, the
Okay.
gravitational force, you need to cancel that force by applying some amount of external force, right? So the same thing,
Okay.
the moment once qt is placed here, already some kind of force is existing. Now I want to nullify, then only I can move. So to nullify that
Okay.
force,
Okay.
I was applying
Yes.
exactly an equal and opposite force. Then the force becomes zero and I can happily move wherever I want. Clear,
Okay.
right?
Yes.
Yeah. So in that case, the differential work done is nothing but minus qt times E into dl. So hence the electric potential is nothing but the work done per charge. So this gives the expression for electric potential. And the units also you can see here, since it is work done per charge, so it is joules per coulomb. Or you can say in terms of your network language, it's a voltage. So the units will be in the order of volts.
Sir,
Okay? Yeah,
this nullifying force will be in the opposite direction. That's why it is negative, right?
correct. Because whatever the direction in which force is existing, you need to apply a force in the opposite direction. That's it. Only you can happily move. Yeah. So this question concept is clear, right? So if you want to find out the electric potential, straight away just integrate the electric field intensity over a differential length. So we already seen what is the electric field intensity due to the different type of charges. When you are integrating the electric field intensity, you will straight away get the electric potential. Now, we will discuss about the concept of the potential difference. The potential difference means what is meaning of that? So this is the test charge, right? This is the test charge actually placed, and the potential difference between A and B. In this section, I would like to find out VAB. First of all, I would like to know what is the kind of standard notation you are following in your network language, because different persons will use different notations. So what do you mean by VAB? It is a potential at A minus B or B minus A.
VA minus VB.
Somebody is saying A minus B and someone is saying B minus A. See, the thing, it doesn't matter. You remember when you are finding out the potential difference, as I mentioned, electric potential is nothing but that, right? So how much work done you need to do in order to move a unit positive charge from one point to the other point. So when you consider the standard notation for the potential difference, it basically depends which is the final point and which is your initial point. So as per the standard notation is concerned, if you see the William Hayes textbook, page number 93 for your reference. So when you consider VAB, they will consider A is the final point and B is the initial point. So the potential difference is always the difference in the final point minus the potential at the initial point. This is a point which you need to be clear. Suppose when you say VB minus VA, that time B is your final point and A is your initial point. But actually, as per the definition is concerned, VAB is nothing but VA minus VB by assuming that B is the initial point and A is the final point. So which means this is minus integral E dot dl. So the lower limit will be initial point and the upper limit will be final point. So when I say VAB, this is the work done in order to move a charge from point B to point A. So B is my initial point and A is my final point. So is the definition clear here? So you don't get confused, you stick on to one notation. So whatever the thing you will say, so the potential difference is nothing but potential at final point minus potential at initial point. So the standard notation of VAB represents first subscript is the final point and the second subscript is the initial. So basically VAB is the work per unit charge when moving from point B to point A. This is the actual definition for VAB. So is it clear? So you can reply. Yeah. So now we'll try to find out the potential difference in case of the different type of charges. So first we'll go for point charge. So first I was discussing about the concept of point charge. So there is a point charge which is located at the origin itself, right? So in the presence of the point charge, there will be a difference in the potential, right? So the potential at B will be different, potential at A will be different. So the point is here, I need to find out what is the potential difference between A and B. So the question is, the potential difference is VAB. So this case I will try to explain. And when you go for the line charge, you try to do it of your own. So let us consider VAB. This is nothing but minus integral E dot dl by assuming B is the initial point and A is the final point, right? So first, what is the electric field intensity due to point charge? So since there is a point charge at any distance of r, the electric field intensity will be Q by 4 pi epsilon r square into AR cap. And what will be the differential length vector? So you can see here, when you are moving from point B to point A, there is a change in rho occurred. You can see here, this is the value will be RB here, and here the value is RA. That means you are moving in a direction where there is a change in radial distance. So I can say dr into AR cap is the dl vector. So dl is basically represents when you are moving from point B to point A, in which direction there is a change occurred. So you can see here from point B to point A, there is a change in R. So that is the reason why I have written it here, it as a dr into air gap. So what will be the VAB right now? So take the dot product of E and dl. It is minus integral q by 4 pi epsilon r square into dr. So lower limit is RB and upper limit is RA. So point B to point A. So what is VAB right now in this case? So VAB is equal to V minus VB is equal to, you can substitute minus q by 4 pi epsilon, and integration of 1 by r square is minus 1 by r from RB to RA. So that is q by 4 pi epsilon into 1 by RA minus 1 by RB. You can cross check that. So when you are separating it, finally what you will get? The potential at A, you can compare this one and this one. So the potential at A is equal to q by 4 pi epsilon 1 by RA, and the potential at B is equal to q by 4 pi epsilon 1 by RB. So when you generalize it, when you have a point charge at any distance of r, I can generalize the equation now. So when you are at point, you are straight away taking 1 by RA. When you are at point B, you are taking it as 1 by RB. So when you consider any point charge at any distance of r, hence I can generalize it as q by 4 pi epsilon into 1 by r. So this gives my expression for potential due to a point charge. So any questions in this slide you can ask. You can ask any questions. So is it clear? Yeah. Someone is.
What if the magnitude of RA and RB is equal and there exists some angle between them?
It will be zero because it is always purely about what is the change in the radial distance happen.
Okay.
You are saying that RA and RB means same, means you are at equal distance from the source, right? But there is a change in angle.
Yes. Between
So
RA and
as
RB.
exactly, I understood that point. The moment once you are always at a equal distance from the source, the potential remains same. That means at point A and point B, if you both the points are in the same direction and inclined at an angle of theta, right? That is what your question.
Yes. Yes, sir.
So when both the distances are same, your dl vector is right away nothing. There is no change in rho. That means your potential difference is straight away zero, because you are moving from the same point and again reaching the same point, because the value of r remains same, right?
Hello?
That means you are starting from the same point where r is same and you are moving into the next point, there also r is same. So it's purely depends on the value of r. Is there any change in the radial distance that is happening? So
No.
that only will change. Yeah. So whenever there is a change in the radial distance, then only your potential will change. It doesn't
Okay.
matter what is the inclination, what is the angle between them.
Okay.
And one more thing I would like to clarify here, and since we have come to this discussion, see here, when you consider any point here, if I want to move from point B to point A, how many number of paths will be existing there? How many
paths.
number of ways are there? Infinite number of ways, literally speaking. Yes.
Yes.
I can move in a straight line fashion. I can move in a curvature like this, and I can move in a like this. I can move like this, right?
Yes.
Now, you have to keep it in mind that the work done is always said to be a conservative. It doesn't depend on when you are moving from one point to another point. It doesn't matter whether you are moving straight line or whether you are moving in a curvature fashion. The integration becomes same. That's what you have studied in your integration also. The work done is independent of the path that you have taken, right? So when you want to move from point B to point A, it doesn't matter what is the direction in which you are moving out. So you can move in a straight line fashion or you can move in a curvature. Even if you move in a straight line, the same potential will result, potential difference. And even if you move in a curvature also, it will result in the same potential difference. So you have to remember here, the potential is basically independent of the path in which you are moving. That means when you are targeting about two particular points, so one point to another point, you can move in any particular path, you will get a finite potential difference. It doesn't depend on the path you have taken. So is it clear?
Hello.
Yeah.
So
Any
because if yes, B and point B it will be zero, right? So that means that input radius, if it is same in the test to other point, if I move, the
No,
outcome
even
is
in that
zero.
case, as long as then also it will be zero. See, this is your point Q, and there are considering 2 points where radial distance remains same. In this case also, whether if you move like this or like this or like this, straight away the potential difference is zero. That's what I was telling. You got the point?
Okay.
Yeah.
Yes.
Your voice is breaking. So what I mean to say was, whatever potential you will get ultimately, there will be a finite potential difference if there is a change in radial distance. That is the first point. And the second point was, whenever you are finding the potential difference between 2 points, the potential difference remains same when you are moving from one point to the other point, either in a straight line fashion or if you move in a curvature fashion. That is what the conclusion here. Now move on to the next one. So consider there is an infinite line charge. This is an infinite line charge located like this. Assume that it is along z-axis. So I have considered 2 points, point B and point A here. So where there is a change in the radial distance from the source. So I want to find out the potential difference here. So you can try this and tell me the answer. Using the same method, what we have done earlier, you try to follow the same. So ultimately VAB is equal to minus integral E dot dl. So the electric field intensity due to an infinite line charge, we already know. So rho L by 2 pi epsilon rho into, can you tell me what is the direction of electric field intensity in this case? The moment line charge is located along z axis, so what will be the direction of electric field?
Sir, rho.
Correct. Because electric field is always radially away from the source. So when you are moving radially away from the source, you are moving in the direction of rho. So I can clearly say here that, so since line charge is located in z axis, the radial is nothing but arrow cap, represents the direction. And when you are moving from point B to point A, you can see here point B is at a distance of rho B and point A is at a distance of rho A. So there is a change in rho that has happened. So d rho into arrow cap. So you can integrate that. So hence VAB is equal to minus integral. So rho L by 2 pi epsilon rho into d rho. And lower limit is rho B and upper limit is rho A, B to A. So what you can say minus rho L by 2 pi epsilon. And integration of 1 by rho will be ln rho, ln of rho. So subjected to the limits rho B to rho A. And I can see here this minus I can replace with a 1 by rho here, because we already know minus ln of x can be written as ln of 1 by x, right? So using that, what you will get, VAB is equal to rho L by 2 by ln of 1 by rho B to rho A. So you can separate it now. So VAB is basically VA minus VB. If we substitute that, so rho L by 2 pi epsilon into ln of 1 by rho A minus ln of 1 by rho B. So by comparison, the potential at point A, you are going to get rho L by 2 pi epsilon ln of 1 by rho A, and potential at B, you are going to get rho L by 2 pi epsilon ln of 1 by rho B. And the moment once you generalize the equation, so if we have a line charge and at any distance of rho, the potential equation I can give like this: rho L by 2 pi epsilon into ln of 1 by rho. So this is the generalized equation for the electric potential due to an infinite line charge. So any questions you can ask? So anyhow, this derivation part you are going to get it in presentation also. You need not to worry about that. But the main fundamental concept only you need to understand here. What is the approach you are following? So to find out the potential difference, just we are simply integrating the electric field intensity over the differential length. That's it. So any questions you can please ask? Clear. So we will move on to the next last case, surface charge. You can see here there is a surface charge located at x equal to 0, which means in a YZ plane. So consider this is having a rho s coulomb per meter square. And you know that since x equal to 0, the perpendicular direction will be x-axis. So can you tell me what is the direction of electric field because of this surface charge? What will be the direction of electric field because of this surface charge? In which direction electric field will be lies? Yes, correct. Yeah, because we already seen, it depends once again on the position of observer also, right? Suppose if the observer is here and this rho s is positive, electric field will be upwards because this charge is trying to move away from the source. And if the observer is here, it is trying to move down. So, but it doesn't matter, when you are moving up or down, there is a change in x happen. So whenever there is a surface charge, the flux will be radially something like this. So electric field is, let us say electric field is located along the x-axis. So first write down the vector. Electric field intensity will be rho s by 2 epsilon into cap. I was assuming since both the observers point B and point A are in the positive x-axis side, I was assuming electric field in x direction. And what is the dl vector right now? So when you move from point B at a distance of xb and point A at a distance of xa, so there is a change in x happen. So straight away you can say dx into x cap. So you can integrate it. So VAB is equal to minus integral E dot dl. So that will be minus integral rho s by 2 epsilon into dx. And the lower limit is point B and upper limit is point A. So what will happen? VAB is equal to minus rho s by 2 epsilon into integration of constant is x, xb to xa. So this finally it will become minus rho s by 2 epsilon into xa minus xb. So what is the meaning of that? VAB is same as VA minus VB. So this you can write it like this: minus rho s by 2 epsilon into xa minus rho s by 2 epsilon into xb. Just I was splitting it to make it as a generalized equation. So the potential at A is equal to minus rho s by 2 epsilon into xa and the potential at B is equal to minus rho s by 2 epsilon into xb. So similarly, if we generalize it now, so when you have a surface charge at any distance of x, the potential is straight away minus rho s by 2 epsilon into x. So this gives the equation for potential due to a surface charge. So these three cases are very important here. So we have seen the electric potential due to point charge, line charge and surface charge. So you can ask any questions. So is the concepts are clear? Or am I going fast?
Sir,
Yeah,
this need not to be always x, right? If it is y-axis and it is in that direction, then
correct,
we can
correct.
analysis differs.
It depends on what is the orientation of the surface charge. So just to give an example, I was considering it that the charge is located in the x equal plane. So this x gives a finite amount of the distance. It depends on the where the surface charge is located. Depends on that you have to take.
Okay.
Yeah. Now, here so far what we have done, the moment once you know the electric field intensity, you are integrating the electric field intensity to get the potential. Now this is the reverse case. So there are some cases where you know the potential, from that you have to derive the electric field intensity. So how to do that? So first of all, what is the relation between electric field intensity and electric potential? So we know electric potential is the negative of line integral of electric field intensity. This is what we know. So from this case, if we want to find out the electric field intensity, what you need to do? Can you tell me what you have to do right now?
Derivative.
Can you exactly name it? We already know what is that. Differentiation is nothing but rate of change, right? So it is basically nothing.
Yes.
It's
Gradient.
yeah. So if you want to get the electric field intensity, it is nothing but a rate of change only. But you need to consider the rate of change in all the directions. So if it is x, y, z, you consider dou v by dou x, dou v by dou y, dou v by dou z. So simply we already know that word. That rate of change is nothing but the gradient. So since because of this negative sign, I have put negative here. So the electric field is nothing but the negative of the gradient of potential. So the electric field is basically the negative of the gradient of potential. So in any question, suppose if they give the potential and you want to find out the electric field intensity was, just take the gradient and put the negative sign. So that actually gives your electric field intensity. Now, just for an example, consider the potential varies only in one direction. So then in that case, I can say, let me say it has only in x direction, right? So if you take the differentiation in that case, what will happen? The differential potential is equal to minus E dot dl. I was assuming that there is only one variation happening. So what is the meaning of that? dv is equal to minus 1 into, so the product of a bar dot b bar will be ab cos theta. So what is the value of dv by dl in that case you can call? That means the rate of change of potential over a length can be written as minus E into cos of theta. This all this case I was assuming potential is a function of variable. That's it. So then in that case straight away I can say dv by dl is equal to minus E into cos theta. So what is actually theta represents? So the theta represents the angle between your electric field intensity and the path in which you are moving the unit charge. Correct. Is it clear? So what is the meaning of potential gradient here, as the subject says? The gradient of the potential is basically represents the electric field intensity. So the potential gradient is indirectly said to be the magnitude of the electric field intensity. Now, if you assume the potential varies in only one direction, the potential gradient can be written by minus E cos theta. So where theta is nothing but the angle between your electric field intensity and your differential length. That means the path in which you are moving the charge. Now, what will happen when you try to move perpendicular to the electric field? Which means, what is the meaning of that? When theta is equal to 90 degrees, what you are going to get? So cos 90 will be 0, which results your dV by dL is equal to 0. That means there is no change of potential with respect to distance. So in that case, it will result the potential has to be a constant. So when you are moving perpendicular to the electric field, there is no change in the potential occur. So whenever there is no change in the potential means the potential remains constant at all the points. Okay? So when you trace all the points where the potential is constant, those surfaces are said to be equipotential surfaces. So the moment when you are moving perpendicular to the electric field, so let us say you are moving perpendicular something like this. If you consider a point here, and even if you consider a point here, there is no change in the potential difference. That means the moment once you are moving perpendicular, you are always corresponding to the points where the potential remains same. Now, trace out all the points where the potential is same, something like this. That kind of surface is said to be an equipotential surface. So have you understood the concept of equipotential surface? Yeah. Once again, I will give one more example also. You can easily understand that. Suppose if you have a line charge something like this located along z-axis. So what will be the equipotential surface corresponding to this line charge? So the equipotential surface will always corresponding to theta equal to 90 degrees, right? So in other words, the potential has to be constant. So since the line charge is located something like this, your electric, yeah, somebody is answering.
Z-axis, right?
The line charge is located along z-axis. What will be the equipotential surface corresponding to this line charge?
X and Y axis.
X and Y axis,
This is
no,
this
parallel to z. Correct.
yeah,
See,
parallel.
because when you are considering z-axis, what will happen? Your electric field will be in the rho direction, right? So something like this. Now, when you will form an equipotential surface? So the equipotential surface will be formed when you move perpendicular to the electric field. That means when you are moving like this, or when you are moving something like this, what will happen? Always you are at an angle of 90 degrees to the electric field, right? So when you are moving parallel to the z-axis something like this, where your electric field vector will be always 90 degrees to the surface. So this is basically nothing but your cylinder, right? So when you trace all the points and join it all together, it forms an cylinder. So with respect to a line charge, the cylinder, when you are moving on the surface of the cylinder, it forms an equipotential surface. So when you move everywhere here, something like this, from here and here, what will happen? Whatever the potential at here, everything will remain same. Can you tell me in other words, why the potential remains constant here? So suppose this is the point A and this is point B. So in one case, you can say that since you are moving perpendicular to the electric field, whatever the condition I have written, dV by dL equal to minus E cos theta, right? So since theta is 90, dV by dl has become 0. That means there is no change in the potential when you move from point A to point B, because always at 90 degrees angle. Can you tell me in other way why the potential is not changing? Rho is same. Exactly. Correct. So when you are moving from point A to point B, I already given. The moment once you are at equal distance from the source, there will not be any change in potential. The reason was, if you go back to the line charge, the potential equation I have given. Rho L by 2 pi epsilon into ln of 1 by rho. You see at point A and point B, both are corresponding to the same value of rho. So the moment once rho is same at point A and point B, what will be the difference in the potential then? There will not be any difference here because rho will be constant. So the potential at A and potential at B will be same. So finally, I will not make it very complicated. So I will try to put it in a simple words. When you perpendicular to the electric field vector, you always move in a direction where there is a no change in potential. And the second point is, when you trace all the points where the potential remains constant, that will indirectly form equipotential surface. Have you understood? Somebody is asking me to repeat. So first point is here, the potential remains constant. First point, when you move perpendicular to E, right? This is the first thing. So when you move perpendicular, so irrespective of the position, you will not get any change in the potential. The second thing, you trace all the points by moving perpendicular to electric field. That means you find the locus of all the points by moving perpendicular to the electric field. It will indirectly form an equipotential surface. Equipotential surface means name itself indicates when you move on the surface, there is no change in the potential. So the potential is the same irrespective of the position on it. So for example, I will give one more example to understand this. So there is a point charge here Q located at origin. So can you tell me what is the locus of points where you are at equal distance from the source? That means, what is the meaning of that? I want to form an equipotential surface. What will be the case in this case?
This is the sphere surface.
Exactly, right. Now you understood, right? When you are moving on a sphere, what will happen? Everywhere the radial distance remains same. Everywhere the radial distance remains same. So since radial distance is same, the potential here, the potential here, the potential here, everything is same. So with respect to a point charge, you can consider the sphere is an equipotential surface, right? So indirectly, the equipotential surfaces will be exactly when you are moving at any point on the equipotential surface, something like here, you are at equal distance from the source. Indirectly, it is called a symmetrical surface. So when you move on the surface of equipotential surface, you are always at a equal distance from the source. Is the concepts clear?
Yes.
Yeah. So that is what the potential gradient represents. Now the last one we will discuss about this electric dipole. Electric dipole means basically, you can see in the dipole antennas kind of thing, it is almost quite related to that. So the dipole is nothing but two equal charges with opposite polarity separated by a small distance. So the electric dipole is the combination of two similar and opposite charges separated by a small distance. So one is plus q and the other one is minus q separated by a distance d. In this case, I have placed a dipole in the direction of z. Now the first thing was I need to find out the potential due to this diode at very far away from the source. So I have considered the value of R much higher than the separation between the charges. In this case, what about the potential at this point? So the first thing was I need to find out what is the potential at this point, and later on I will find out what is the electric field intensity also. See here, this positive charge will also create some electric field and negative charge also will create some electric field. As long as the observer is very far away from the source, you can say that all three rays are looking to be parallel. Am I correct? The moment once the observer is very far away from the source, you can see here that all the three rays are looking to be parallel. Is my assumption correct or not? Yes. So the moment once you are very far away from the source, you cannot see the source at all. You can assume that all are coming from the same point. So that is the way I am saying that all the three rays are looking to be parallel. So when you are very far away from the source, what will be the electric potential? I will generalize it here. So the potential at this particular point is due to the potential because of positive charge plus the potential because of the negative charge. It is just only because of two charges are existing here. So the potential due to the positive charge will be straight away Q by 4 pi epsilon. We have seen in case of point charge. Q by 4 pi epsilon into 1 by R is the potential. So from the positive Q, you are at a distance of 1 by R1. Plus, what is the potential due to negative charge? Minus Q by 4 pi epsilon into 1 by R2. So finally, if you simplify the potential, this is nothing but Q by 4 pi epsilon 1 by R1 minus 1 by R2. So that is Q by 4 pi epsilon. You can calculate R2 minus R1 divided by R1 R2. So what will happen when you consider a point very far away from the source? That means your R is much higher. Can I do the approximation something like this? R1 into R2 can be approximated to R square. Is my assumption okay? The moment when you are very far, R1, R2 are both are similar, looks to be same. So R1 into R2 can be approximated to R square. And what is the value of R2 minus R1? Ideally speaking, it is close to 0, right? But instead of making it as a 0, I was saying here, I was making in terms of D, separation. I was assuming that D is very small compared to R. So we will get a very small value, but not 0. So let me write that value. See here, this is your R1 and this is your R2. So the difference R2 minus R1 is nothing but you draw a perpendicular line here. So this portion represents the extra difference, right? So when you draw a perpendicular line here, after this one and this one both are same. So whatever the change in R1 and R2 represents only this particular portion, right? Now, since you know that this is angle theta and this value is also said to be theta. So there is a right angle triangle here and you can see here this particular triangle. So this is the particular triangle where D is the hypotenuse and this is your theta. So R2 minus R1 is adjacent to the angle. So I can say R2 minus R1 can be approximated as D cos theta. Any questions here you can ask? So do you have any questions?
But what will be this theta angle? Means like
No, theta is not. Why I was mentioning theta means theta is basically what in spherical system?
okay.
Theta is the
Coordinates.
angle measured from the z-axis, right? So this is also I was assuming it is from the z-axis. So we measure the angle from the z-axis. Yeah. Yeah. Now, so I can say R2 minus R1 can be approximated to D into cos theta. So I can substitute in this equation. So what is the potential you are going to get? So Q by 4 pi epsilon. So R2 minus R1 is d cos theta divided by R1 into R2 can be replaced as R square. So this gives the potential equation in case of an electric dipole. So we have to remember one point here. So whenever there is one point charge only existing, the potential is Q by 4 pi epsilon into R. So potential proportional to 1 by R if it is only one charge. But look at this equation. Whenever it is a dipole, the potential is directly proportional to 1 by R square. Because there are two charges, the potential is proportional to R power n. So where n is equal to 2. So you need to understand the difference. So the same thing QD cos theta, I was expressing it as two vectors, something like this. QD dot product with some radial direction divided by 4 pi epsilon R square. So you can see here if you want, what is the dot product of QD and AR cap? So dot product of A bar and B bar will be straight away mod A bar mod B bar into cos theta, right? Now mod A bar means QD itself. So that is already verified. And modulus of AR cap means nothing but the unit vector along this particular direction. So the magnitude will be 1. So modulus of A will be QD and modulus of B is 1 and the cos of angle between them. So the angle between D and R is straight away. So this is cos theta. So whatever the same expression I have got here, I was trying to represent in terms of a vector. So one will be the charge into displacement. The 2 into D, I was representing it in vector. And the other vector is the radial direction. So the reason being why I have written like this was, the product of charge into displacement is basically called the dipole moment of the electric dipole. So the electric dipole moment dot product with AR cap by 4 pi epsilon into R square. So if you know the dipole moment, straight away you can use this formula to calculate the electric potential. So where the dipole moment is basically given by the charge into the displacement vector. So units will be in the order of coulomb meter. So is it clear? So once you know the dipole moment, you can straight away use this formula to get the electric potential. Suppose if you know the charge and distance separately, and you can use this formula. So you can ask any questions you have.
So what exactly is the dipole moment?
Dipole moment is basically nothing but, see, dipole moment actually you will get it basically in case of a dielectrics. So the dipole moment is basically says how easily the dielectric material can be polarized. Simply, suppose if you consider any dielectric medium, there are different type of dielectric mediums are available. So something like polarized dielectrics and non-polarized dielectrics. So whereas if you consider a non-polarized dielectrics, straight away you can say there is no dipole moment. So when you consider a polarized dielectric mediums, there exists already a series of dipoles will be existing in that medium. So whenever the dipole moment is basically high, if you say that, the permittivity of that particular medium is high. So the dipole moment is a measure of the relative permittivity in a dielectric medium. That is one of the example I can say.
Means we can say that higher permittivity means dipole moment
Higher
will
dipole
be.
moment in case of polarized dielectrics.
Okay, only in case of okay.
Yes, yes. Yes.
And the non-polarized mean there is no opposite charge.
Yeah,
Only one single
non-polarized
charge is there.
dielectric. Actually, what will happen in a polarized dielectrics? Generally, we know that dielectrics doesn't conduct any current, right? But what will happen in case of polarized dielectrics? When you take any dielectric, try to apply some external field. So you place the dielectric medium in an electric field. So whatever the dipoles are aligned inside a dielectric medium, they are trying to align in a particular direction. So the dipoles are trying to start align in a particular direction. It is going to create a counter electric field. That is basically called a polarized dielectrics. Whereas in case of a non-polarized dielectrics, if the dielectric medium is placed in electric field also, the dielectric, whatever the dipoles inside there, it will not be oriented in a linear manner. So it will be completely in a disorder. So polarized dielectric means the dipole can be aligned in the presence of an external electric field. That is called polarized dielectrics. Non-polarized means the external electric field has nothing to do with the alignment of dipoles inside the medium. So which will doesn't cause for any electric field. That is a special topic we will discuss when you the capacitance also. That is very important topic. So any questions you can ask still? So now we know the electric potential due to a point charge, right? That is QD cos theta. Just a minute. So there is a potential, you know that formula, QD cos theta by 4 pi epsilon r square. So you try to find out the electric field intensity using the gradient. So E is equal to minus del V. So you know the potential equation in spherical. So find out the electric field intensity. So I'm sorry for the interruption. So you know the potential, you try to find out the electric field intensity just by applying the gradient. So in case of a gradient, we already know in case of spherical system. So you can apply that formula. So that is the rate of change in R into air plus 1 by R into dou V by dou theta, A theta cap plus 1 by R sin theta, dou V by dou phi into A phi cap. So you can find out the value E is equal to minus 1 into QD by 4 pi epsilon is a constant, you take it outside. So dou V by dou R means, so cos theta is also constant, and differentiation of 1 by R square is minus 2 by R cube into air cap plus 1 by R into 1 by R square is a constant, and differentiation of cos theta is minus sin theta, A theta cap. So you can simplify that and rearrange it. So you will get QD by 4 pi epsilon and take R cube as a common and get 2 cos theta into AR cap plus sin theta into A theta cap. So this gives the expression for electric field of a dipole. So this is the same equation even if you go for an antennas. I think whoever has completed the antenna part, you can see the same equation. This is the electric field generated by a dipole antenna. So you need not remember this equation, just you can see the application. Once you know the electric potential, how to calculate the electric field intensity. So here you can go through this derivation. So any questions we have? So what is your plan? You tell me right now. So will you go through theory part of this class, and then in the next session we will discuss the problems? Is it? Because I think you require some time to go through the theory and remember the formulas, I felt. Or else if you are interested, I will discuss the problems in the now also, not a problem. So I think better you go through the theory part. So you go through the lecture again, because a lot of derivations are there in today's lecture. So first you go through what is an electric potential. That is a main crucial topic we have discussed. So go through the expression for electric potential due to point charge, line charge and surface charge. And once the potential is known, we have come back to the potential gradient. So potential gradient indirectly says, you know the electric field intensity and find out the electric potential. And we have learned the concepts of the equipotential surfaces. And then we have seen the concept of electric dipole. So please go through all the concepts. The moment once you are familiarized, and then if you are memorizing the formulas, it's easy for you also to understand when I was discussing the problems. I think that will be the better part. So go through the theory part, then we will discuss the problems in the next Sunday. Yeah. You have any questions? We will discuss now.
Yeah. Hello?
Yeah.
I've known reference that electrostatic air fields. That thing house and
No, your
not
voice is
understanding that.
breaking.
Why?
I'm not able to. Your voice is some break is there in voice. So okay, you can type here in the chat box. I'm able to see. So others also, if you have any queries, you make it ready. We'll try to discuss here. So electrostatic field is irrotational. Yes. Correct. Correct. So that is what also I have explained in case of Maxwell equation also, right? So you can see here, suppose when you have a point charge here, so whenever their electric field is existing, if it is a source of electric field, the electric flux lines are always said to be divergent nature. Have you seen any kind of rotational nature for electric fields? Rotational nature means it should start and end at the same point. So will it happen for electric field? No. So which means that when you consider any electric field vector, there is no rotational nature, which means that the curl for that particular vector is 0. So is it clear? So since there is no rotational nature exists for electric field is basically said to be irrotational. So the meaning of irrotational was there is no rotational nature exists for electric fields, right? So that is basically said to be the first Maxwell equation we already seen. And the same equation I forgot to discuss in the last time. We try to understand the meaning of conservative, right? So when the curl becomes 0, the electric field vector is also the conservative. That I will try to explain right now. So the same equation, when you see in the integral form, you are getting integral E dot dl is equals to 0, right? Now, so what is the meaning of integral E dot dl? So electric field is volt per meter and dl is nothing but meter. So it is nothing but an voltage. So in other words, the electric potential basically integral E dot dl represents some amount of voltage. Right. Now, you are getting, whenever the loop is closed, the net potential is getting it 0. The same reason today also I have explained. So when the loop is closed means, what is the meaning of that? You are starting at the same point and again trying to reach the same point. So finally, you are starting from the same point and ending from the same point. So your initial point and final point both are same. So when initial point and final point both are same, there is no change in the potential. So that's what it says. So when you are starting from this and try to reach again same point, there is no change in the potential happen. That's what we studied now also. So that's the reason why the potential becomes 0. Because both are corresponding to the same potential. So the difference will be 0 when you are moving in that way. So the meaning of conservative was, what is the meaning of conservative? This is already says your Kirchhoff voltage law. So in case of a Kirchhoff voltage law, if you have a source and if you have a load like this, two resistive loads, what will happen using your KVL? Whatever the source voltage will be there, that will try to apply across the both R1 and R2. So the meaning of conservative was there is no wastage of energy. Suppose whatever the power is driving by this voltage source, it will be completely absorbed by both R1 and R2. That is happened because your KVL is satisfying. So your KVL is satisfying means there is no misuse of the energy. So you would have been studied about conservation of energy also. So energy will be transferred from one form to the other form. So in the same way, here the voltage, whatever it is generating here, it is driving the energy, and these passive elements are absorbing the energy. And there is no loss of any energy there. That is because of your KVL. So since the net voltage has to be become 0, whatever the total drive voltage here, it should appear across both R1 and R2. So there is no change in the potential. That means there is no wastage of the potential. So that is the reason why your electric field is said to be conservative. So conservative means when you go a loop, the net voltage should become 0. That is what the nature conservative says. Any question? Still?
Hello.
Yeah.
So that the non-conservative field does not hold energy. Means if it is energy, it will that radiate the energy. If it is that non-conservative.
Yeah. But all the electric field is conservative because see here, when you go in a loop, if something is generating the energy, that full energy will be absorbed by some other elements. That means there is the voltage will not be missed out in case of when you are considering any loop. So there are active sources are there, passive sources are there. Whatever the voltage generated by the active source is completely absorbed by the passive source. So in that case, the net resultant value will be 0. Then resultant value will be straight away 0, right? I was giving 100 volts, and there is a passive voltage absorbing 100 volts, so equal. So the net voltage will be straight away 0. That is what said to be conservative.
Yes.
Yeah.
Yeah.
So any other questions? Okay, then you go through the theory, and we'll see the problems in the next class. Okay. That's it for today. We'll signing off. Good night.
Thank you.